So I think Gensler does a pretty good job talking about a lot of the basics of inductive reasoning. Um, the stuff with inductive syllogisms, I'm not going to say much about. I think he does really well with that. What I want to talk about are some of the things he goes over, some of the concepts like independence and being mutually exclusive that I think he goes over pretty quickly. He explains them, but they can be a little tricky, so I want to say more about them because they actually are really important to inductive reasoning generally. And he gives us some pretty cool formulas to do some stuff with inductive reasoning, but you have to keep these distinctions in mind before you can apply these in any kind of intelligent way. Okay, so here's an example. Let me, a lot of these are going to fall back on gambling. Gambling's the easiest for a lot of these, so sorry. So, or maybe you love that. I don't know. I had a student a couple semesters ago when I mentioned that these were going to be, on gambling. He seemed checked out for most of the semester and just like instantly for the first time he perked up. Anyway, gambling's an easy one, so they will be about that. So here's a question, and how do you answer this? What are the odds that you draw? Imagine I shuffle the cards, cut the deck, and you draw a card. What's the odds that it is a king or a queen? How would you figure that out? Well, Gensler gives us a rule to do this. When A and B are mutually exclusive means A and B can't happen together. Then you just take the odds of A plus the odds that B. When you say, what is the chance that A happens or B happens? A draw a king, B draw a queen. Plug in anything you want here, right? They're mutually exclusive. If I draw a queen, it can't be a king. If I draw a king, it can't be a queen, right? So I can just use this formula. Odds of drawing a king from a well shuffled deck, 1 out of 13. 4 out of 52. If you remember your high school math, you can reduce that down to 1 out of 13. Odds of drawing a queen. There's 4 queens in the deck of 52 cards. Also 1 out of 13. Because these are mutually exclusive, because whenever you draw a king, you don't draw a queen. Whenever you draw a queen, you don't draw a king. You can just add these. Well shuffled deck. No other cards have been drawn. Draw a rant. You just draw to start with from that. 1 time out of 13, you're going to draw a queen. 1 time out of 13, you're going to draw a king. Well, what are the odds you draw a king or a queen, one or the other? Just add them together, 2 out of 13. Now, look, I think it's really cool that Gensler goes over this, but he goes a little quick because he just throws out this idea of mutually exclusive, and he doesn't really say enough about it. And I want to say a bit more about it. When A and B are mutually exclusive, that means if A happens, B absolutely does not. And if B happens, A doesn't, right? Think back to our Venn diagrams. If I say A and B are mutually exclusive, how would you handle that? Well, you just black out the center. There's no case where something happens that's both an A and a B when A and B are mutually exclusive. Compatible, not mutually exclusive, well, that just means our center isn't blacked out. There can be stuff in there, right? So look, that's really abstract. I think what helps for most people are examples. Here's some examples of mutually exclusive things. Someone passes a class, they get an F, right? Different schools have different rules. I think in some rules for some things, D might be passing, but F is never passing, right? No school for no program is F ever a passing grade, right? Somebody passes, they don't have an F. If they have an F, they don't pass. Mutually exclusive. If I draw a king, I can't draw a number card, right? If it's a king, it can't be a number card. If I'm rolling 2 die, if I roll 4 on 1, then I can't roll a combined total of 3 on both, right? Because whatever comes up on the second one, it's going to be higher than 3 because I've already rolled a 4, right? It's snowing outside. It's 95 degrees, right? It is, as far as I know, physically impossible for it to be that hot and for it to snow, right? Snow hits, even if it were snowing higher up and it hits air that's that hot, it's going to melt. It's going to turn to rain, right? Born in China, born in North America, right? China is in Asia. If you are born in China, you are not born in North America. If you were born in North America, you are not born in China. China's just not on our continent, right? Believe in God, be an atheist, right? By definition, an atheist is someone who does not believe in God. So if you're an atheist, you cannot believe in God. The two are mutually exclusive. All right, so we might talk about compatible things, right? And compatible just means not mutually exclusive. That's all compatible means. Compatible means two things can happen together. If we were drawing a Venn diagram, the circle is not black. The middle part is not blacked out. Pass a class, get a B, right? Lots of other ways to pass a class. You might get an A, you might get a C, but, you know, if you tell me you passed the class, it's quite possible you got a B, right? If you draw a king, it is quite possible it's the king of hearts, right? Two are not mutually exclusive. It's a bit unlikely. There's only one card out of 52 that is both a king and a heart, the king of hearts. It's unlikely, but it can happen. They're not mutually exclusive. You roll two dice, and you get 4 on one. Is it possible you could still get 7 when you add them both together? Yeah, there's a way that can happen. The other die can come up 3, right? Not likely, but it can happen. It's snowing, it's 25 degrees, right? Now look, it can be snowing and it can be a little warmer than 25, it can be a little colder. There's lots of times it's 25 and it's not snowing, but they're compatible because they can happen together. Born in Mexico, born in North America, right? If you are born in Mexico, you are born in North America. The two can happen together. Believe in God, be a Zoroastrian, right? Zoroastrian, it's a smaller religion, but Zoroastrians do believe in God. So the two can go together, right? You know, not everyone who believes in God is a Zoroastrian by any means. There are Christians, Muslims, Jews, you know, lots of religions believe in God, but these two can happen together. You can believe in God and be a Zoroastrian, right? In a way that you can't believe in God and be an atheist. All right. Now remember, we can only use this addition rule, A or B happening, what's the odds, when A and B are mutually exclusive. Think about that, memorize that, because it will be important. Okay. So let me give you an example of some obviously bad reasoning. And I want you to tell me what's wrong with it. So the odds that I draw a red card from a well-shuffled pack of cards, 1/2, right? 13 out of the 52 cards are diamonds, 13 are hearts. That's 26 out of 52, 1/2. The odds that I draw a number card, well, 2 through 10 are number cards. 9 number cards in every suit, 9 number cards diamonds, 9 are hearts, 9 are spades, 9 are clubs. You reduce that and everything, 9 out of 13 are number cards. 36 out of 52, right? But I've reduced this down. So odds that I draw a number card or a red card, 13 out of 26. For a number card, all right, sorry. So I draw a red card or a number card, red card, 13 out of 26, number card, 18 out of 26. Add them together, 31 out of 26, 119%. Now, obviously, something has went wrong here, right? When you see odds above 100%, you know that a mistake has been made, right? Odds cannot be greater than 100% or less than 0. If it comes up less than 0, that almost never happens even when you make a mistake with the math. Much more common is you get higher than 100%. If that happens, you know there's a mistake somewhere, right? This is impossible, so where's the mistake? Well, the problem here is that these two are not mutually exclusive, right? There are a lot of cards that are red that are also number cards, right? 2 through 10 of hearts, 2 through 10 of diamonds. They are both number cards and red cards, right? So what's happened is that we count the number cards twice because they're part of both groups. Well, how do we make sure we don't do that? Whenever events are compatible, we have to take the odds that A plus the odds that B and subtract the odds of A and B. For compatible events, A or B equals odds that A plus odds that B minus the odds that both happen together. So, go back to this one, we fix the math, right? Red card 26 out of 52, number card 40 out of 52, but we also have red and number card, 9 heart number cards, 9 diamond number cards, 18 out of 52. So we add red card, 26 out of 52, number card, 40 out of 52. Then we subtract the overlap to make sure we don't count them twice. 48 out of 52, 12 out of 13, roughly 92%. With the stuff about odds and probability, I don't care that you put it in terms of percentages. I really don't. I honestly, it's a weird preference. I don't even like percentages that much. I think fractions are honestly, once you get used to it, easier to deal with. But, you know, you can do percentages because you can punch those into a calculator, make your life easy. I do not care. Percentages, fractions, either way, doesn't matter to me. So 12 out of 13, 92%. If you're really, really hung up on fractions, which some people are. Or sorry, on percentages. So anyway, I hope the basic idea makes sense. The important thing is to think about, are these mutually exclusive or not? Make sure you have a really good glue on this idea of mutually exclusive versus compatible.